Hello, everybody. Looks like we're almost at time, so I'm going to get started because there's a fair amount to go through. Hi, I'm Nick Rabinowitz. I'm a engineer on the visualization team here at Uber. And I'm going to talk about H3-js, which is the JavaScript bindings for our H3 library. And I'll talk a little bit about what that is in case you missed some of the earlier talks today. Just very, very small amount about me. I've been primarily a front-end developer for over 20 years now. I've been at Uber for about 3 years. I'm currently the maintainer of H3-js. So I've worked some on the core H3 project, and then I've worked a lot on the JavaScript transpiled version. So just what we'll cover in the next 45 minutes. I'll give you a brief intro to H3 in case you missed the sessions earlier on. It'll be pretty brief. There's a lot more about it online and in other documentation. I'll go through the actual H3-js library and a few of the core functions. This is going to be fairly code heavy. All of my examples are in Observable, and they're all published. Observable, if you're not familiar with it, is a sort of, it's basically a JavaScript version of Python notebooks. So it's a live coding environment, and you can go in yourself, you can change the values, and you can see what comes out. If you have a laptop, want to follow along at home, feel free to do so. You don't need to do that for this workshop. So I'll go through what's in the library briefly. I'll go through the basics of one method of rendering hexagons on a map. There are lots of methods, but I picked the easiest one, and I'll talk a little bit about it. And then I'll build up in a couple steps towards an example app doing a suitability analysis, which is the kind of thing that's actually fairly advanced GIS approach, hard to do with other things, very straightforward to do with H3. So what is H3-js? If you saw any of the talks earlier today, you might already know the answer. But basically, it's Uber's hexagonal grid system. So it's a geographic geospatial indexing system where you can uniquely identify any point on the Earth as belonging to a grid cell, which in this case is almost entirely hexagons. This allows you to essentially geocode things either at a very coarse level, as you can see these sort of almost continent-sized hexagons here, or down to a very fine level. The finest resolution that we allow is resolution 15, which is about a square meter. So it gives you this ability to identify the grid cell for anything on Earth, identify the position of that grid cell on the Earth, and this allows you to do a lot of bucketing and other transformations of your data that would be hard to do if you're just using points. The way I usually think about sort of geographic grid systems is that it takes all this messy, difficult to work with geospatial data, things like admin boundaries and lat-long points, and turns this into this really clean mathematical space that's really nice for running algorithms and other kinds of analyses. H3 has hierarchical resolutions, which means that every coarse cell has a set of children at each level below it. It has 7 children in the next finer resolution, 49 children in the resolution after that, and so forth. And that's also the process we use for identifying the index of a cell. So the index of a cell is basically the 0 through 6 number of the cell at every point in that resolution hierarchy. And the library comes with a whole bunch of useful algorithms. I'll go through a few of them. They mostly deal with things like traversal, so finding the neighbors of a given cell, and dealing with things like regions, so transforming between polygons and hexagons. So let's get started. This is the short link for the workshop itself, t.uber.com h3-js-workshop, or you can probably find it on the Observable site. From here on in, I'll be out of slides and into Observable. And this is the actual site you can go to directly if you missed the link. So a quick intro to H3-js. H3-js is JavaScript, but it's actually not a port of the C library, but a transpiled version. So we used mscripten to take the C code, transpile it to JS, and then write some bindings around that to allow you to invoke the C functions. The nice thing about that is it means that all of the logic is exactly the same as it is in the C library. There aren't any discrepancies. So you can basically use H3-js the same way you would use H3 in any other language that we have bindings for. The core of the library are the functions that give you the H3 index for some geographic coordinates, or give you the geographic coordinates for some H3 index. An H3 index is a 64-bit number, which we usually encode as a hexadecimal string, because JavaScript can't deal with 64 bits. And you can see it looks like this. And if you, I can't do this with one hand. You know, if you give it different coordinates, you'll get a different H3 index. This last parameter here is the resolution. So this is resolution 9. It's about a city block. For a while, this was the sort of semi-standard resolution that we used at Uber, because it's about the right resolution for a lot of our data. But you can use any resolution that makes sense for your use case. The reverse of this gives you the center of the hexagon. So it gives you a latitude, longitude point for any given index. You can see that this is a lossy transformation. My data coming in could be much finer granularity than the center of the hexagon it falls into. And so that's one thing to consider, is that usually when you're transforming points to hexagons, you get some data loss in terms of your accuracy, but you gain a lot of things in terms of your ability to work with that data and your ability to bundle different points together. This last part, H3 to geoboundary, gives you the vertices of an H3 index, and that allows you to draw the hexagon on a map or using other kinds of visualizations. There's also a set of functions for dealing with a hierarchy. So H3 to children gives you the descendants of a given cell. Every cell has, as I said, has either 6 or 7 descendants. This is the resolution you want to get it at. So right here, I've got a resolution 9 hexagon, going to resolution 10, and I've got 7 children. If I change this to resolution 11, now I've got 49 children. That's the grandchildren of my original cell. And we can go in the opposite direction as well. H3 to parent gives you the ancestors. In this case, I'm going from 9 to 7. I can go all the way up resolution 0, and that's the base cell for this hexagon. These are useful for various different things, and one useful property of H3 is that this is just an extremely fast operation. It's a bitwise operation. So even in JavaScript, the implementation of this is millions of operations per second. And as I said, we have a bunch of functions for traversal. So one of the reasons we chose hexagons instead of a square grid system is that you get this really nice property of a hexagon, which is that it has 6 unambiguous neighbors. And so if you want to do anything that involves moving around neighbors and spreading data out across your neighbors, for example, or buffering your cells, or doing a lot of other kinds of transformations, having unambiguous neighbors is very helpful. If you think of a square grid, I don't have a graphic for this right here, but if you think of a square grid, squares have 4 unambiguous neighbors, and then these 4 corner neighbors that are kind of ambiguous, and it's harder to deal with them. And they usually need a different treatment from the direct neighbors. So K-ring basically gives you the filled ring around a given center hexagon. Hex ring gives you the hollow ring around a given hexagon. And this second parameter is the radius. So if I change that to radius 2, now I have 19 hexagons that are all in the ring around the original hexagon. And the hollow ring, if I change it to 2, I've got 12. That's the hollow ring of all things that are all hexagons that are 2 steps away from my origin. This is all a little abstract when I go through it here, but it'll get concrete fairly quickly when we start rendering things. I also have a function to give me the distance in grid cells between 2 H3 indexes. And I've got a bunch of functions to deal with regions. In the rest of this tutorial, we're actually going to usually use a utility library that kind of uses these inside of it. But H3 polyfill is a way to go from a polygon to a set of hexagons. So if you have a geographic polygon, for example, describing the shape of a country or a county, You can fill that with hexagons, get the set of hexagons that are within it. And if you have a set of hexagons and you want to get the outline, you can use this H3 set to multi-polygon. The reason why these aren't totally symmetrical is that if you have an H3 set, it might be multiple different polygons if they're not connected. There's a lot more functions in the H3-js library. I won't go through them all now. But if you're actually here, or if you want to look at the GitHub for H3-js, it gives a full list of the APIs for everything. So now, that's all fine and good if you want to look at code, but if you want to look at hexagons, we need to start rendering things on a map. And as I mentioned before, there's a lot of ways that you can render things, but I'm going to go through a fairly straightforward one using Mapbox.gl. And I won't go into all the details of using Mapbox.gl because Mapbox.gl has great documentation, but I'll just briefly go through one simple way of doing this. You can see I'm actually rendering hexagons in two different ways here. I'm rendering these colored shapes. So these are filled polygons. And then I'm also rendering sets of hexagons as an outline using that H3 to multi-polygon function that I mentioned previously. The data I'm using here is just dummy data. And what I've done here is simply take one hexagon, take the K ring. So this is the filled ring of all hexagons within a distance 3 of this center. And then I've made it into this kind of object where each hexagon index is associated with a value. And here I'm just using math random. And we'll get into sort of using more realistic values later. One nice thing about math random is that it's between 0 and 1, which makes it easy to deal with the data later. And as I go through this tutorial, I'll be normalizing everything to 0 and 1 just because it simplifies rendering. So now I have this object. There are lots of other data structures that could work here, but an object is a nice way to associate a hexagon with a value. I'm going to render a map. As I said, I won't go into great detail on exactly how this works. This is actually taken from the, some of it, this is observable specific. It's taken from the observable tutorial on how to use Mapbox.gl. But basically, I'm making a new map. I'm attaching it to this container that I made up here. And then I'm using these render hexes and render areas function, and that's where the actual meat of rendering the hexagons is going to occur. The very TLDR here is each of these is making a GeoJSON object out of the hexagon map, and then it's using Mapbox's built-in styles to render that GeoJSON on the map. So for every set of hexagons, in this case, to render the hexagons, I use this utility library. This is another open source library that Uber put out called GeoJSON to H3. And it's fairly straightforward. All it really does is wrap the core H3 functions to make dealing with GeoJSON slightly nicer. So this H3 set to feature collection basically gives you one feature per hexagon. And then we can assign some properties to each feature. In this case, I'm assigning the property of value to that value that I pre-computed earlier. I add this GeoJSON source to the map, and then I add a rendering layer. Mapbox has these two ideas in its style rendering. There's the source, which is your actual data, and the layer, which gives you paint properties and allows you to render one source multiple times in different ways. I'm assigning it some basic paint properties, and I assign them some more paint properties down here. This stops syntax. This is a computed color, basically, where I'm saying use these 3 colors, and if it's 0, use the first one. Interpolate between 0 and 0.5 to get to the second color, and so on to the last color. And then I can also change the opacity and various other properties. So that gives me these colored hexagons. And if I change or re-render this set of random values, I'll get different hexagons colored in a different way, but using the same map scale and re-rendering the map. What I'm doing with the outlines is, and I'll go through why this might be useful later, but in this case, I'm saying, I actually care most about values above a certain threshold, and I care about the regions that those hexagons define. So when I go to render the areas, I'm going to do this filtering operation on my hexagons. I'm going to take only the ones above a certain threshold, and then I'm going to use those to do H3 set to feature, which will basically turn those H3 hexagons into a polygon describing their outlines. And now I have this nice way to paint an area on the map describing a set of hexagons. And I won't go through in detail, but I use the same basic premise of adding the GeoJSON as a source to the Mapbox.gl map, and then adding some paint properties for it in a layer. I'm also referring sort of under the hood to my basic configuration object, which is just some configuration for this page, and to these set of dependencies. So probably should have covered these up front, but they're sort of below the fold because you usually don't have to think about them much once you load them. Mapbox.gl obviously is the map library. H3 is the H3-js library, and then GeoJSON to H3, as I mentioned, is this utility library for dealing with GeoJSON. So that's the very basics of rendering hexagons. As I said, there are multiple ways to do this. This is using built-in native Mapbox rendering for GeoJSON. There are a lot of tutorials about how to do that. You can also use DecGL's rendering for GeoJSON, or you can use other approaches for using, for example, instanced values in DecGL. And there's trade-offs between these. I tend to think that the Mapbox one is easiest if you're not planning to do any animation or things that need to respond quickly to user input. The main downside of the Mapbox stuff, it's extremely performant for things like pan and zoom, but it can't animate very quickly because it requires a whole sort of map refresh. But for most semi-static data sets, the Mapbox styles are a perfectly good way to go. And it's nice because they don't introduce any additional dependencies on something like DecGL. So this is fine and good if you have your data provided in hexagons as this little hexagon to value map. But you're probably not going to be using input data that comes in hexagon form, unless perhaps you work at Uber and you're producing a lot of hexagon-based data at the outset. If you're using public data, for example, most of the things you're going to be dealing with are probably going to come in as polygons or come in as points. So the next question is, how do we take some data set that's encoded in, using a different geodata format and get it to hexagons? The really nice thing about using a geographic grid system at all, and H3 falls into this category as well, is that once you have multiple data sets moved into a grid system, you've got a common unit of analysis that you can use for everything. That allows you to join data sets that are otherwise difficult to join. It allows you to do things that require a unit of analysis with equal area. So if you wanted to, for example, like take some population in a polygon and spread it across different pieces of equal area, the H3 cells give you a really nice way to do that. And it allows you to express it at different resolutions. So in this case, this is resolution 8, but I can re-express this at finer granularity, down to whatever granularity makes sense for me. The trade-off is usually one of accuracy versus processing time. The more hexagons you have, the harder it is to render them, the harder it is to do the data processing. If I wanted to show this at meter resolution, I couldn't do it in the browser. But if I want to show it, at roughly city block, I can do it fairly quickly. So you have to make your own sort of trade-off decisions about what resolution you use. And the other question, of course, is whether you have some data that's coming in at the hexagon level and you need to align with that resolution. Your mileage may vary depending on your own application, but it's nice to be able to choose a different resolution that works for you. So the data I'm using here is polygon data that comes from Uber's movement data set. So this is a data set of travel times. And in this case, I've sort of grabbed travel times specifically for Oakland. I think these are called, now I've forgotten it, travel analysis zones. There's some city planning defined polygons. And I've grabbed travel times from Oakland to downtown San Francisco. And each of these is, a polygon, and each of them has some properties, including this travel time in seconds from Oakland to downtown SF. And so what I want to do is I want to convert these all to sets of hexagons. And I'll do that over here. And it's really pretty straightforward. I take each of these features, I run it through the inverse function from GeoJSON to H3, feature to H3 set. That's going to give me a set of hexagons that falls within that, that polygon. One really nice feature of the polyfill function, the way that the algorithm works is very simply to take the center of the hexagon, and if the center of the hexagon is inside the polygon, then you give it, that is included in the set, and if it's outside the polygon, it's not included in the set. That means that you will have some hexagons that go outside the polygon, some hexagons that are inside the polygon, but it has this nice feature that if you bring in contiguous data, like polygons that all align perfectly with each other, you'll come out with contiguous sets of hexagons. There's no hexagon that's going to be assigned to two different features here. And so in this case, all I'm doing is making the same kind of hexagon to value map, and I'm just copying the travel time here from the polygon to my hexagon. This makes a lot of sense if you're dealing with kind of rate data, something that's evenly distributed across the polygon, where the value is the same at every part of the polygon. If we were dealing with something additive, like population, for example, then I would have counted the population as many times as I have hexagons, which is probably the wrong choice. And I might want to divide by the number of hexagons I have. That's one approach, for example. So if I was using population here, I'd probably use this, divided by hexagon's length. Oops. See how bad my one-hand typing is, which would give me values where the actual value was a little bit closer to what you might have in each hexagon. As a side note, this is something quite hard to do if you're not using a grid system, is if you don't have equal area, then you have to start weighting each sub part of your polygon with its area, and you have to compute the area for every part of the polygon. It's really easy with hexagons because they all have the same area. And the last thing I'm doing here is, as I said, I'm normalizing it. And that's just a sort of quick process to take all the values and move them between 0 and 1. That's sort of a convenience function for me because it makes it easier to render. I don't have to compute this domain when I'm going to change my color styles. But it also makes it a lot easier if you want to bring multiple data layers together. And I'll get to that a little bit further. So, whoops. Oh, yep, thank you. I took my, well, I'll move on in any case. But now I have my polygons. I think I screwed them up when I started playing with the division. Revert. It's a nice feature of observable that you can revert to the last published version. This is what I want in the end. Great for polygons. What happens if you want to use point layers? In this case, I might want to think about BART stations, for example. BART stations come in as points. I have the locations for them. They're not polygons necessarily. And I might want to show them on a map. Now, obviously, I start off kind of looking at just what's the hexagon that every BART station falls into. So I'm loading, again, a GeoJSON feature collection. Every item in this feature collection is a point, has a lat long, has some additional information about the BART station. And they don't have any data associated with them. I'm just going to treat each one as, a single value as 1. And all I'm going to use here is this sort of count points thing. So I go through every feature, I find a lat long, I encode that to an H3 index, and I add 1 to that index. Now you can see that most of these just come up with a value of 1. Some of them, you might have places where you have 2 BART stations, or in this case, I think I might actually have entrances as well as exits or something like that. So I might have 2 things in the same hexagon, or that might be 19th Street and 12th Street, not sure. But you end up with binning. So instead of just having a single hexagon for every BART station, some things will get counted with more than one station, especially if you start making the hexagons larger. Now, especially if I have fairly fine-grained hexagons, this isn't going to be super useful for combining with other data sets because I only have a single hexagon for every BART station. And depending on what kinds of analysis I'm interested in, I might care more about the distance from that BART station. I might consider a BART station as having a radius. In the little example that I'll give after this, the sort of sample app, I care about walking distance to a BART station. And obviously, this data set is only going to tell me information if I live right in the hexagon or if I'm walking right from the hexagon. So in this case, I want to do what in GIS terms is usually called buffering, spreading out the data for that BART station and putting it in a larger radius. This is something H3 makes very, very simple. It can be difficult in other kinds of systems, and it's not great even in a square grid system. But if I want to buffer the points, get something like this. So now each of these is buffered. All I have to do is take the K-ring for each one. The K-ring, remember, is that filled ring around a central hexagon. So my buffer points function looks really a lot the same, except instead of taking only this index, the H3 index for each station, I'm taking the ring for a given radius. And I'm adding every hexagon in that ring to my outcoming data layer. You might notice here that one issue here is if I bring in a radius as a number of hexagons, I say, I want a radius of 2, then it's going to be very dependent on my resolution. If I want to have a common distance radius, I can do that pretty easily. And I made a little utility function here called km to radius. All it does is take this H3 edge length function, which is basically a metadata function provided by the H3 library. Tells me what the edge length is in kilometers for any given resolution. And now I can convert some kilometer input into an edge length, and I can use that for my radius. And so here I'm using this km to radius. I'm saying I want everything within approximately 1 kilometer of my BART station. Now you can imagine with something like walking distance, or as it happens with something like surge, you might want to have some decreasing function as you get further away from the point. And again, this is something that otherwise might be quite difficult. H3 actually makes it really simple because we have these functions to give you increasing numbers of hollow rings out from that point. So if I change this from my buffer points function to this buffer points linear function, I can get these sort of decreasing areas of influence out from every BART station. And this might be something where if I think that the value increases as the closer you get to the BART station, for example, I think BART stations are better the closer you are to them, and over here the influence isn't very useful. I can use this to overlay them and get these useful points of density where you're close to a lot of BART stations. The way I'm doing that, again, is fairly straightforward. Now, instead of taking a single ring, I use this K-ring distances function, which is going to give me the set of concentric rings coming out from that single origin. And then for every ring in that set, I'm going to add the ring to my data layer with a decreasing step function. So I'm basically taking the distance times a step and removing it from my my data value. You can easily imagine there are lots of other functions we could use here. We could use other kinds of interpolation. You could use basically any easing function. It's the same thing as you would use for animation easing or any other kind of transformation. But in this case, I'm just using a linear one because I'm lazy and it was simple and perhaps easy to explain. So now I've got a few different ways that I can represent points and I can represent polygons. And what I wanted to do in the last part of this is go through a little app that I made as an observable notebook demonstrating suitability analysis. Suitability analysis, if anyone has a GIS background, it's this fairly straightforward analytical approach. I like it because I'm not a data scientist, and it appeals to me because it's really pretty simple. You just take a bunch of data layers, you smush them together, you add up, you sort of add them up vertically. If you think about them as a layer cake, you add them up vertically, and you show the result of that vertical addition on the map. And then if you care more about certain layers, you can weight them more or less heavily. One of the things I really like about this is it gives you this nice subjective ability to say, well, I care more about this than that, and I can see what happens when I change the weights of my different inputs and make different decisions based on that. Suitability analysis in the GIS world is very commonly used. I think the classic example is store locations. You know, I'm Starbucks and I want to know where to put my next Starbucks. And I might want to be far away from other cafes, or I might want to be close to other cafes, which I believe is what Starbucks used to do, like right across the street from your competitor. You know, or I have other things that might matter to me. And in fact, I probably have this whole set of parameters that I want to consider. I want to be close to cafes. I want to be close to public transportation. I want to be, you know, whatever you have. Maybe I want to be in high income neighborhoods or something if you're Starbucks. I have no idea. And basically a suitability analysis allows you to take all these different sort of inputs of interest, mash them together, and come up with some composite view of the geographic area you're considering. H3 makes this really easy because it makes it very simple and straightforward to join geographic data sets. You put them all in this common unit of analysis, a hexagon at a particular resolution, and then you can just sort of mash them together. So this map is my suitability analysis, very ad hoc for places I might want to live in Oakland. I like Oakland. It's a good place to live. And some places in Oakland are better to live than other places in Oakland. I picked some relatively random layers of things I might care about. Again, very idiosyncratic. I've got some crime. I've got schools because I have kids and I might want to live near a school. I've got BART stations because I want to be close to BART. I'm taking that travel time that I had because I want to be able to have low travel times into the city because I work in the city. And I also really like cafes, so I added some restaurants and cafes to this as well. And what I've done here is to give you a little weight slider for each one. And so if I decrease the weight of schools, I get a different picture of the city overall. Maybe I care less about being close to BART because I know I'm always going to have to drive. Or maybe I care, conversely, less about travel times because I know I'm going to take BART. Or I know I'm going to bicycle. And so this gives you the ability to sort of quickly investigate a bunch of different layers together. And just to go through it in a little bit of detail, I'm basically using the same techniques that I just used to encode all of my data into hexagons. Some of these are not coming in GeoJSON format, and so I'm doing different kinds of transformations, but they're all using pretty much the same idea. I'm creating this normalized map with values between 0 and 1. For prime, I'm adding 1, but then I weight it negatively because prime is bad, so I don't really want it added as a good thing to my map. For schools, I'm giving a hex ring around it because I care about being not necessarily right in the same hexagon as the school, but close to it. For BART, I'm using the same buffer points linear function that I demonstrated in the last one. For travel time, I'm doing exactly what I did in the polygon example, except I'm taking the inverse of the travel time because I want lower travel times to be better. And finally, for cafes, I'm just taking only the individual H3 index because I want to be right next to a cafe. I want to be able to walk to it every day, sit there, drink my cappuccino. Now that I have all these layers, I can basically just add them together. So here I have this array of all my layers, and I'm associating each layer with a weight. Obviously, these could just be numeric weights. The nice thing about observable is that it gives you this ability to really easily make a user input that can be associated where you can use the resulting output in the rest of your sheet. So each of these is just this little slider input, and this output variable crime weight is a number that this slider represents. So I have this set of all my layers. I've associated a weight with each one, and then I just run them through this combination function. And the combination function is really straightforward. It's basically a reduce, though I did it here as a for each. I'm going to run through every map layer, in each map layer, I'm going to run through every hexagon, and I'm going to put it into this combined map with the value in that associated with that hexagon weighted by the particular weight I've given that layer. I'm going to normalize the result, so I have values between 0 and 1, and I have this resulting map. And I can see this map at different layers of granularity very easily. Because none of my data comes in as hexagons, it's very easy for me to change the granularity on the fly and make different choices. And I can adjust the weights, and then I can investigate. So when I adjust the weights very tight, I get this highly granular picture. That might be too granular if I'm looking for an apartment or a home. When I get a little bit less granular, I get this sort of broad heat map of the city, places I might want to live, places I might be less interested in living. And it also gives me some sense, when I combine this with my own sort of intrinsic knowledge of the city, it might give me some sense of what data sets I might be missing. You know, here we get very high weights around Oakland City Center. That's great. Oakland City Center is great, but maybe I don't want to live right downtown. Maybe I care about living in a less densely populated area. And I could bring in that as a separate data layer if I wanted to bring in, for example, census data. And again, I could also, right here, I'm still including all this BART stuff. If I only care about Oakland, I could also run this through a filtering pass. So with some of the analyses we do at Uber, we basically have a mask of hexagons. One common use here is I don't want water area in my resulting data set. So I'm going to run it through this mask, which is basically a set of hexagons that I'm going to filter out. The really nice thing about using something like H3 from a computational standpoint is that these are all just set operations. I can really easily take data out or add new data in just by running it through a union or other kind of set operation. And here, down here, I have all the sources for all the data I'm using here. Again, these are somewhat arbitrarily chosen for the example, but you can imagine taking in as many additional layers as you want. I had to actually resist the urge to just keep on bringing in more and more layers, because once I have the basic setup here, it's really simple to add more and more modular layers and start getting more and more levels of detail here. So that basically covers the suitability analysis. And the nice thing about this is I've done this in the GIS world using, Esri and ArcGIS. And it can be very difficult to do, because when you are mashing together polygons and raster data, you have to worry a lot about map projections. You might have to, when you're doing points, you have to, buffer them, but you might not be able to do this like decreasing step function. It can be very difficult to do unless you convert everything to a raster. H3 makes it quite simple, because it just gives you this single unit of analysis at a level of granularity you choose. Whoops. I don't know what just happened, but I lost it. And you can add them all together. And apparently I just lost my Zoom connection, but that's convenient because I also was done with my presentation.